Right, and today, as we said, it's all about the earth and how do we regenerate carbon in the soil, and of course, absolutely fantastic what Blaine sort of said, because there it is, there's actually the simple, the totally natural, total practical way, and here's nature, putting carbon in the soil, here's Blaine putting carbon in the soil, 27 tonnes per acre. And as we sort of said yesterday, as is Mother Nature, it's simply CO2, sunshine, plants, putting that fixing that carbon as plants, and then putting it in the soil. And really the challenge now is, how do we do that on every square foot, every handful, every acre across the planet? And remember, yesterday we more or less sort of started with our friend Charles Keeling 50 years ago, and Charles, of course, had shown us that exactly this was happening. And of course, here's our emissions, and here's our carbon drawdown. And of course, what Blaine has sort of showed us that, yep, okay, he is in the carbon drawdown business. Okay? And the question really now is, all right, how do we extend that? Because we know, as a consequence of Charles Keeling, there's a symptom of the gap between the emissions and the drawdown activities on this planet at the moment. CO2 is going up because of this imbalance. And our challenge now is to say, how do we increase this drawdown, increase what Blaine has shown us he can do, because we've now got to basically say, here's 10 billion tonnes of carbon per annum that we have to draw down to stay level, but we don't want to just stay level, we want to actually drop CO2 over time. And so the answer is we may have to take down another 10 billion tonnes of carbon per annum of heritage or legacy emissions. So the challenge is, can we draw down 20 billion tonnes of carbon a year globally? And as Blaine has shown us, that yes, we can. We can do it so successfully, so simply, so naturally, and actually so profitably. I think that's a very, very important thing. Actually, I might move this way, because then more people can see it. There's people here. Oh, okay. It's like, I don't know if you know the joke. They built a big opera house in Warsaw, in Poland, right? And a really glamorous Baroque opera house, but they only had one opera there, and then they demolished it because nobody could see anything. Wherever they were sitting behind a pole. Right. The children say, hey, Dad, that's lame. That's really lame. Okay. But the point is, that's the challenge, right? And again, as we talked about yesterday, you see, that's exactly the challenge that Mother Nature had, because basically CO2 started off at 950,000 parts per million 4 billion years ago. And of course, how does it draw down? How did it draw down to the 280 parts per million that occurred a couple of hundred years ago? And in a sense, it's that biosequestration of carbon. Initially, most of it went into, as we mentioned before, Blaine mentioned, in the Arctic, into all the corals, into the carbonates in the oceans. Some millions, some billions of tons of carbon was put into the oceans, into corals. But then, as we said yesterday, 420 million years ago, we had the oceans, we had the rock, bare rock. CO2 was about 8 to 10,000 parts per million. And of course, it's the vegetation on land through this drawdown process that brought it down. And our challenge is now simply, all right, well, look, how do we extend this in terms of the rate, but also the area of land that we can regenerate and draw down carbon on? And of course, we can look at nature and say, okay, well, what is the carbon drawdown potential or activities that nature does through exactly the same processes that Blaine's using? And the best I've ever sort of seen as far as carbon drawdown potential was in Papua New Guinea on the Fly River. and that's all rainforest, right? But it's all tropical rainforest in the Fly Rivers, this river. And it was water hyacinths. You know, it's an aquatic weed growing in the Fly River. It had been introduced as a weed species, so, you know, it had this weed vigor sort of thing. And it was doing 500 tons of biomass per hectare per annum. And all of that, because it's an aquatic weed, was in a sense breaking down and going into organic oozes. So that was about 300 tons of carbon per hectare per annum.
Walter, can you take 1 second break?
Yeah.
It sounds like Eric's having an
Okay.
issue with the microphone.
So what I'm saying is nobody's suggesting that we've got to go anywhere near that. But what I'm saying, Mother Nature, is able to do this at prodigious rates. And of course, we know that she can because in the last sort of 420 million years, we've taken about 20,000 billion tons of carbon from the air, and we put it into soils, we put it into vegetation, or she did, soils, vegetation, peat, methane hydrates, and there's about 20,000 billion tons of carbon that's been biosequestered.
How about Azolla?
How much can Azolla do?
Well, I mean, Azolla apparently has done a lot.
Oh yeah, no, not quite as much as the water hyacinths, because it's got a bigger surface area root interface, but it'll do, you know, okay, well, let's go, we can do some others on that. But not quite up there, but it's getting prodigious amounts, 100, you know, easily 100 tons.
Did you say 300 tons or
300 tons of carbon per hectare per annum, and I'm just saying the biological, you know, the capacity of green biomass under ideal conditions to fix carbon, you know, that might be sort of coming close to the plateau ceiling.
We should not be intimidated.
No,
Big range here.
no, but when people tell you you can't do it, or you can do 0.1 ton, then you sort of say, well, hang on a minute, you know, there's a lady over there who does a lot better than that, right? But coming to farming,
Oh, I'm sorry.
Yeah,
We lost you.
we lost you.
Oh, you hit the off button.
I hit the off button, see? Right, now I'm on.
I mean, listen to
You've been lost, but
You're all
now you're
on.
found.
Now, okay.
Sorry, earlier you had said 500 tons carbon. But then-
500 tons of biomass.
Oh, okay, yep,
Okay, and there's about multiplied by 0.6.
okay.
Because that's roughly, you know, well, it depends, different types of biomass, but that's roughly the ratio of carbon in biomass, right? Biomass is carbon, hydrogen, and oxygen,
Yep,
some nitrogen, and
okay.
again it comes down to 0.6 if you're converting it to carbon.
Okay, and does some of that get released as well, or?
Yes, okay, we'll talk about that later.
Yeah, okay.
Some of it does. In this situation, not much, because it's all anaerobic, it's all then sinking as oozes in the river, right? And it just builds peat and organic oozes and land. Very quickly it
Okay.
builds land, right?
Thank you.
But in most cases, some of it is oxidized, but we'll come into that, it's very important. But talking about farming, again, we've got innovative farmers, in the case of sugarcane farmers in Mackay, Queensland, and see Simon Matheson, he'd be doing basically 173 tons of biomass above ground per hectare per annum. And okay, that's above ground, but we also know there's another 173 plus tons below ground, because, hey, plants don't just grow above ground, that's all we see. But of course, plants have roots, but actually the fundamental thing with plants, actually, we need to say that, it's so important. See, we always see things above the ground, and basically above the ground we might see 30 to 40% of the total biomass carbon. 30% is in roots, but the really significant thing that mostly we forget, 30 to 40% is exuded as exudates from the roots. Okay? And so these are sugars and amino acids and polysaccharides that are being exuded from the roots, because these things are feeding the life in the soil. They're feeding that microbial life. And so when we do our counting, because we're Homo hubris above the ground, we often just see this part, the above ground. We don't recognise the enormous sink of carbon that's going into the ground.
Walter, excuse me, the below ground, the 173 tons,
Yeah.
that includes the exudates?
Yes, that would include the
So
exudates.
it's root mass and
yes,
exudates.
so what we're saying,
Okay,
in this
thank you.
case, conservatively 50-50, right?
That include, okay, because
So what
you're
we-
saying 30, 30, and 40, so the 40 is the exudates.
40, yeah, up to 40% in exudates.
So the
right?
30 is actually root mass.
Root mass, and then 40 is up to
And
exudates.
above is
And above
173.
is just
below-
biomass.
Below 173 and another 200
Okay.
or so
Yeah, and
is
so,
exudates.
spot on. So we're saying roughly here's 350 tons of biomass, which is roughly, 200 tons of carbon per hectare per annum. So what I'm saying, there's a farming system, again, able to sort of put prodigious amount of carbon, fix a prodigious amount of carbon. Again, it's not the issue of who's got the biggest amount, it's just saying that these potentials exist.
Imagining myself in a sales situation with a land manager trying to
Yeah.
sell the concept, I imagine that land manager saying, well, okay, maybe that happens in New Guinea, but
Yeah.
not on my, in my mix of plants
Totally.
on my land. I can't believe it's happened.
No.
So the question is, is there any referenceable material about typical plant mixes on typical,
Yes.
in typical climatic and use, where you can say, yeah, this does it with this mean and that standard deviation, this
Exactly.
is what you can
Exactly,
expect.
yeah, no, and so I'm just setting biological potentials, but now, exactly your point, Tim, I think we're now sort of saying, okay, well, realistically, and Blaine sort of mentioned it, he sort of said 27 tons of CO2 per acre, so you multiply by 2.5 to get to hectares.
No,
And of
that's
course-
per hectare. Right.
Oh, that's per hectare, right? That's per hectare?
3
Okay,
tons per
good.
acre.
But that's about
of
8
carbon.
tons of carbon per acre,
Well,
because
he's
you
talking
divide by
CO2.
3.7, right? To get CO2 back to carbon.
Right.
So it's about 8 tons of carbon. And so this actually answers Tim's point. We have got innovative farmers all over the world, and of course Peter's been leading globally in this carbon, a challenge to sort of document this. But people have been doing, the 8 to 10 tons of carbon per hectare per annum. The innovative farmers are doing that, and that was the point, Tim, that I think is so important. We're saying here's the ceiling, but here's actually good, innovative practice consistently, whether it's in Canada, Australia, US, UK, whatever, right?
And that's net after whatever got burned
That's,
out in the
yes,
farming process?
Yes, and we'll come into that in a minute. That's the residual carbon sequestration potential.
Can you quickly do the calculation for CO2 converted to carbon, the ratio or molecular?
Okay, well, look, I mean, it's simple, like CO2,
Uh-huh.
CO2, and obviously then we're looking at the carbon, and obviously we've got carbon, and then we've got 2 oxygens, so the molecular weight, and so you've got to divide by 3.7. Okay, so you're dividing by 3.7 to turn the weight of carbon dioxide into carbon, right?
Just
Or
roughly-
conversely, if you want to turn carbon into CO2, you multiply by 3.7.
Roughly a third.
Yeah, roughly a third. Okay, and so the answer is nature. This is what nature can do. This is what innovative farmers can do. But the real punchline is that our industrial agriculture as a whole is losing 5 to 10 tons per hectare per annum. Okay, so we're still in a sense oxidizing and losing carbon from most of our industrial agriculture at the rate of 5 to 10 tons carbon per hectare. So we're just trying.
Is that net 5 to 10?
Yes, we're losing net 5 to 10, right?
So
Because-
why isn't all soil reduced to sand and dust?
Well, we are rapidly
getting there.
doing a lot of that, Tim. Yeah, absolutely. And okay, and we've been very successful. 5 billion hectares for this planet, 13.9 billion hectares of land has been turned to desert and wasteland by us through exactly this carbon degradation oxidation process, right?
Tim, in my case, At settlement in 1880, we were at 12% organic matter. Most farms would be between 2 and 5 today. So we've taken it from way up here right down to here.
Yeah.
Most industrial farming is more like 2.
When you say 2%
Yeah.
carbon,
Organic carbon.
Organic matter.
Okay, yeah, so it's sort of like 0.7%. Yeah, okay.
Yeah.
Yeah, something like that. Certainly in Australia, it's much worse than that. I mean, most of our industrial farming, because we didn't start so well, is down to about 0.5. Right? It's sort of getting really down to that mineral sort of sand level. And as sort of Blaine sort of said, it can't hold water, it doesn't make nutrients available, it waterlogs, it's, you know, it's all the problems, it's all the symptoms coming from that carbon degradation.
So I have one more thing, Walter. In the carbon farming solution, Eric Tonsmeyer's given a lot of numbers for different kinds of farming.
Yeah.
I do not agree with that, as I don't agree with your numbers on sugarcane. I think it has to do with the microbes or the sponge.
No, okay.
So
No, look, and yes, we'll go into exactly into that, because, see, the question now comes, it's not whether you're zero tilling, it's not whether I'm growing sugar cane or wheat or whatever, I expect to get this. There's much more sophisticated processes, because some people grow, sugar cane and they can do this, other people grow sugar cane and they're still losing carbon. Depends how you grow it. And just in a little while, that's exactly what I want to get into, you know?
Same thing with raising cattle.
And the same thing with raising cattle or anything, you see? And so I want to get into what are the processes that govern that, and what are the land management factors that both build carbon, and what are the land management practices that degrade carbon, right? So it's not just what we grow and it's automatic, and that's in a sense the problem. So, you know, Didi was saying she was in Oklahoma, there's people been doing a management practice for 10 years, and hey, it hasn't had any effect on building soil carbon. And of course the answer is yes, we can explain that, because it's the processes that are important, not just what you're growing. And this is terribly important for governments, you see, because in the past government said, can I just nominate what type of agriculture it is? Is it zero till or is it what? And can I give it a nominal carbon increment score? And the answer is no, you can't. And of course that's where they've really come unstuck. You really have to, as Peter's been doing, you really have to go to each piece of land and then do the diagnoses, look at it and say, what are the processes that are working here? How do I help the farmer change the processes to get to whatever level they can get to, and then measure that level. It's not making an assumption that, that farming system will automatically deliver something.
Can I just comment? You mentioned Eric Tonsmeyer's book and on carbon farming solutions, and that's had a lot of press. And I do respect what Eric has done, and I think what he says, is the data that he presents is there, but I'm not going to try to change any data, but there are other data points as well. And he is pretty much, I think, tropical centric in using mostly plants as basis. And I think it's important to consider that when you're considering that particular source. It doesn't really get you a lot of solutions either, as far as practical solutions. And it does have little bits on grazing and cropping and things like that. But I think there's a lot more to the story that he wasn't able to present. So I hope you can keep that. That's just one book, and there's a lot more to the story.
He also gets stuck on 200 billion tons of carbon is the max that the world soils will hold. And
No, I agree. And look, in a couple of minutes, let me give you the process, the microbiology toolbox to make this thing sing and dance for you, right?
Yeah, I'd suggest that Walter has a way of telling a story from beginning to end, and let's hold off on questions for a little while and let him tell that story,
so,
and then we can figure out what's missing.
And of course, just again, being on the positive side, we can again go back to nature, right? Because where we're sitting, and certainly where Blaine is, see, 9,000 years ago it was under ice. right? We still had the Ice Age. And see, those prairie soils in America and in Canada, they formed, 9%, 10% organic matter plus meters of depth within 9,000 years. And so therefore, you look at the prairies, and again, you look at how much tons, and if you calculate that, and we've done it, varies from some, that's easily 10 tons carbon per hectare per annum that nature has done in building those prairie soils over the last 9,000 years. In Kalimantan, which is Borneo, tropical Borneo rainforest, sea levels rose dramatically about 6,000 years ago. And so now we've got peat rainforest in Kalimantan, again, 10 metre deep peat rainforest, and we know that those peat forests have formed in the last 6,000 years because that's when sea level rose to create that new land surface in a way. Actually, the Indonesians are clearing their rainforest, they're burning the peat, and there's sometimes, often finding there's no land there. They're back to water. You understand? Because the whole land was peat. But again, we know this was 9,000 years, 6,000 years in Kalimantan, and again, this was sort of 12 to 15 tons of carbon per hectare per annum. And so we're just trying to say, okay, Kalimantan. And so there's plenty of evidence. The Bronze Age in Ireland, Scotland, basically we've now got radar sensors, and they pick up archaeology of old stone fences below the soil surface. Where basically the Celtic people 4,000, 5,000 years ago had built little crofting farms. But now that's under 4 metres of peat. You see, they're looking through 4 metres of peat to pick out the stone fences. And if we assume the stone fence was 1 metre, 3 foot tall, again, we've got 5 metres of peat, so they're 5,000 years, and we've got, we've got 5,000 years, and we've got then, 5 metres of peat, and again, it comes to well over 10 tonnes. So what I'm trying to make the point is there's plenty of cases in nature and natural regeneration where we can establish these sorts of figures occur. Charles Darwin in 1871 did a beautiful little experiment in his woodland, and basically he just put down a layer of lime, which was in a band that he could see, and he did that in 1859. He came back in 1871 and he measured how much soil the worms that he was passionately studying towards the end of his life, how much soil these worms had created. And of course, again, he created this depth of new soil, and then he worked out what the carbon level was, and his figures was 11.2. Okay, so basically all I'm trying to say here is that those figures of 10 tonnes per hectare per annum that the innovative farmers are doing are totally consistent and substantiated by what nature has been doing and the documented evidence of nature doing that. Okay, so I think we made the case, or I hope I can make the case that yes, we can sequester carbon. I mean, I didn't really have to make it because Blaine had basically confirmed that beforehand, very simply, very naturally, but it doesn't happen everywhere. And so what I want to talk about now is exactly what you were asking. Okay, what are the processes that govern this, and how do we understand those processes, and how do we then manage our soils to fix carbon through these microbial processes, rather than just assuming that we're going to get it from growing wheat or whatever. And actually it's very simple, and it's as very simple as A, B and C. Okay, so it's a very simple situation. And what we'll do is we can just draw a little plant here. It can be grass, it can be anything, and these of course are our root systems. And all of agriculture, and we'll call A agriculture, is focused in a sense, where we are, above the ground, right? We are visual animals, we walk above the ground, so our whole focus above the ground is maximizing plant growth. And I'm a scientist, I was a young scientist in the Green Revolution, and it was all about growing more faster. Okay, can I grow more per hectare? Can I grow bigger plants? Can I grow them faster? And so our whole fixation is actually, biomass above ground through, of course, plants, photosynthesis. And as we sort of said before, there's the figures from sugarcane, or there's the figures from, water hyacinths or whatever, what the biomass above ground is. And in a sense, our whole mind, our whole culture is focused around, hey, we've got to maximize A. But that's not what's important, because what's important is not how much carbon we fix through photosynthesis, it's what happens to every molecule of carbon that is fixed. Okay, what happens to it? And in a sense, for the last 420 million years on land, every molecule of carbon that's ever been fixed by photosynthesis by plants has only had two choices. Well, it doesn't have a choice. I mean, two things can happen to it, right? Two things. It can either burn, oxidize, dies back to CO2, or it can be sequestered into stable soil carbon. Okay, it's that simple. Two options. Does it oxidize, does it go back to CO2, or does it sequester into the soil as humates, glomalin, stable soil carbon? We'll come into that in a second. Okay, and all our farming system, our industrial farming system, is all in this oxidation box. Because if we are burning stubble, if we're cultivating, if we're fertilizing, and if we're using biocides, or if we're fallowing, okay, all of these things are actually pushing CO2 back up into the air. All of them are operating through oxidation. And basically our industrial agriculture is, doing 120 to 150% of the carbon that it fixes, that those plants on that hectare fix, they're pumping them back into the air. Obviously we're using massive amounts of fossil fuels to do all these, destructive things. And in a sense, the embodied emissions, and if we add those to it, it could even go higher. Basically it's come a bit off it now, but we were using previously 10 units of oil energy in industrial agriculture to produce 1 unit of food energy. So we were massively subsidizing this industrial agriculture out of cheap oil to produce food. And all of that was driven up by CO2.
Walter, just for the non-scientists in the room, can you just say what oxidizing is?
Okay, oxidizing is simply burning, right? It's simply taking cellulose, or it's taking plant material and burning it, and it oxidizes either rapidly through burning, or it can go slowly through microbial breakdown. And that's actually an important thing. There are microbes that drive this thing, so not all microbes are, in a sense, helping here. There's oxidizing microbes,
I don't know if I might be able to help out, but also all animals oxidize.
Yes, we oxidize as we eat food. We're oxidizing that food because that's how we get the energy from the food. And of course we're exhaling CO2. When we exhale, we're exhaling about 1,000 parts per million CO2.
And that's just simply, that's the oxygen combining back again with the carbon, so that it's from carbon.
Simply the reaction. Okay, we've got CO2 plus water with sunlight. Here is the energy source coming in, makes carbohydrates, C6H12O6 plus oxygen. And that's, in a sense, the fundamental process that governs life on land. CO2 plus water making sugars and producing oxygen. But of course, that's photosynthesis, and going the other way, if we then take this, that's respiration, that's oxidation, that's burning, we're taking sugars, we're consuming oxygen to produce CO2 and water. And in a sense, we as animals are doing this.
And plants also go through cell respiration.
Oh yeah, plants, exactly, for their biochemical processes, they're also respiring. There's a balance here, but what we've been talking about is the net balances, right?
Yep.
When we've been talking about the figures, we've been the residual net balances, right? So what we're really saying here, we have an ecology in our agricultural, in our industrial agriculture above the ground, which is very much about maximizing plant growth. And of course then we're just in this business of adding more and more inputs, and all of these things are driving this oxidation of carbon. And so it logically follows that if we're in this game, no matter whether we're doing zero till or what we're doing, we're losing carbon. And so the point was we're losing 5 to 10 tons carbon per hectare. That's conservative in some cases, okay, but as an average, it's industrial agriculture. And obviously, that's not, that's going to get us back to desert, that's going to get us back to that mineral sand, that's going to get us back to cactus. You see? And as we said, every molecule of carbon has two options. Does it burn or does it biosequester in carbon? So now let's start talking about the C box. How do we do the biosequestration? The first key point is what Blaine sort of showed us, that if we get biomass up here and it's there as litter, and basically how do we turn some of that litter, instead of just oxidizing, how do we turn that back into stable soil carbon? And so Mother Nature said, hey, this is critically important. I need that in the soil as carbon. I need the nutrients from that recycling. So it invented these biodigesters. And because that litter is spread everywhere, it needed a mobile biodigester. So it basically designed these leg things to move them around. And then it designed an intake end and had some ears on it and some eyes on it to sort of basically, because a biodigester, it needs to know what it's sort of biodigesting, so it needs to take that in. But then it also had to design a business end, right? Because the business end of the biodigester is this stuff. Okay? And so the first lesson is what Blaine told us, isn't it? Whether it's chickens, whether it's pigs, whether it's cattle, he's got mobile biodigesters. Now, all he has to do, he's lazy, all he has to do is go there for 5 minutes and move the fence. You didn't have to build them, did you? The bastards self-reproduce. Bloody biodigesters everywhere. Okay? And anyway, so that's the elegance, that's her elegance, Mother Nature, right? So we've got these biodigesters. So with that, instead of burning off a lot of the litter, and again we had that on the previous page, which may be, if this is 30% of the biomass, it might be half of that, might be 15% of the biomass, if we haven't taken the wheat off or whatever, all the stubble and stuff like that. Can we use these mobile biodigesters to turn that into biofertilizer? Okay, that's a positive. And can we turn that into humates, right? Because some of the excrement is sort of humate products. The other big factor is we've got all these roots. We said there was 30% of the biomass roughly in roots. And there are a whole group of fungi in soil, higher fungi, that again turn these into humates. Okay, and these higher fungi are Basidiomycetes. There's special groups of fungi, and then they rot down lignin, they rot down cellulose, but they, instead of just rotting them down to CO2, they actually break them up and polymerize them, which means they link them all up in long, big molecules, chains, called polymerization. And the bigger these molecules get, the more stable they get. Okay, so these humates are just basically long, massive molecules of carbon, hydrogen, oxygen, but they're all joined up as big networks, and because of the size of the molecule, they become more and more stable. And in a sense, it's these humates that then have formed the peat or the stable soil carbon, the peat, the brown coal, and then of course the black coal. And literally we have put, basically with peat and brown coal, black coal, some 10,000 billion tonnes of carbon into the world's soils and then landscapes through this carbon drawdown process. There's another category here. We talked about the root exudates going exuded from the roots, and that may be 40% of our total carbon fixation. And these guys are the most important in a way, because these are the things that exude and they feed the whole microbiology in that soil, that living soil bug, diversity.
Sorry, the fungi actually connect with the roots, and so that's why the 30% was involved with the fungi, and then this 40% you're talking about feeding other.
Okay, no, okay, well, I'll just explain.
Okay, yeah.
Yep. Because these root exudates, they are largely in nature commanded and taken by the mycorrhizal fungi, and these things actually then proliferate massively throughout the soil. You're all sitting down except Eric, and 25,000 kilometres of fungal hyphae per cubic metre of healthy soil. Wow. Twice the diameter of the earth in every cubic metre. Thin mycorrhizal hyphal threads proliferating throughout that soil, interfacing with all the soil particles, absolutely fundamental in solubilizing, absorbing, accessing nutrients, and taking up those nutrients for the growth of the plants. And tomorrow we'll be talking about that interface from a human health point of view. But 25,000 kilometre hyphal interface, healthy soils between...
Per cubic metre?
Per cubic metre of healthy soil. Okay? And I've measured them, but you don't actually have a ruler. You do it otherwise.
Wait.
What was the word before interface?
Okay, a 25,000 kilometre interface between the soil, the microbial hyphae, and the plant, right? So it's really quite fundamental because, let's go a bit further. These hyphae are made out of chitin, glucosamine, and they have a membrane, it's like a one big cell, and it's all one tube of selective membrane, and it's that membrane that's then absorbing essential nutrients. So we've got this massive area. So the area is of course pi diameter times length, right? So you've got the diameter is about 20 microns, 20 millionths of a meter, but the length is that 25,000 kilometres. So massive surface area of fungal hyphal membrane absorptive interface, and it's critically, we'll talk about that in detail tomorrow.
So are they visible with a 10-powered magnifying glass?
No,
you're right down
they're 20 microns, 20 millionths of a metre. Sometimes you will see some of it when they form rhizomorphs or strands. There might be 50 of these hyphae knotted together as a rope, and you can start seeing the rope, but you won't see the individual hyphae.
Well, you 400x. We can use a lot.
Oh yeah. You'll see, from 100 onwards you'll see
but
them.
It's tiny.
Yeah, but also they're often translucent. But okay, look, I didn't want to get into tomorrow so much, but basically the important thing about these things, they're made, as I said, out of chitin or glucosamine, and glucosamine, when it rots down, forms a substance called glomalin. And Chris isn't here today, is she? No, Chris isn't here today.
No.
But basically...
He's working on 5 grants.
Okay, no, but it doesn't matter. So there's this other stable carbon substance called glomalin, and that's sort of basically another stable carbon which is fundamental. Remember yesterday we talked about our friends the lichens? They're gone. But the point is that we talked about the lichens, and the lichens again, that symbiosis between algae and fungi, and those lichens left behind organic detritus 420 million years ago in that first petagenesis pioneering event, and that was glomalin, and that's in a sense how soils evolved. Soils started, and from that the whole terrestrial biosystem evolved. So what we've got is then all these sources of stable carbon, and of course we've still got another category some of you are interested in, perhaps called biochar, which is in a sense charcoal as well. And some of this, if it burns and it produces charcoal, yeah, that can also be stable soil carbon, but it's just an inert carbon material. We can talk a lot more about that as well. But the point is that there's a whole lot of carbon, and so we talked about the critical thing is B and C, you know, like the options. And the issue in agriculture, the issue in sustainable farming, the issue in the future food production globally is the ratio between B and C. Nothing's wrong with inspiring some CO2. Obviously we have to reuse it. But if 150% of the carbon fixed is going into CO2, we're going towards desert. But if we can put 50% or 70% of this into stable soil carbon, we're building up natural capital. And that's the critical thing that we're doing in regenerative agriculture. And so when Blaine sort of says, here's my soil, and it's spongy, and I can, you know, it's just full on, it can absorb water, it's well aggregated, contrasting his neighbour that's waterlogged, compacted and what have you, it's basically because of these factors have been built up over the last 20 years through Blaine's management, right? So it's our choice and our management, the ratio between how much of A do we B or how much of it do we C? Okay? It's that simple. I mean, how much, whatever we grow, whatever's photosynthesized, do we burn, or how much do we put into that soil carbon bank? Okay?
Spend or save.
Spend or save. Oh, yeah, I mean, Mother Nature, come on. Yeah, basic. Now, because we drew a square, we've got 4 fields. And so we had this thing D, didn't we? And of course D is also important because D stands for dividends. And this is again Blair's, he's already jumped the gun on this. You see, he says, hey, it's got to be profitable, right? And this is so important, we touched briefly on it yesterday, but let's reinforce it now. Every gram of extra carbon we put into C can hold up to 8 grams of extra water, because that's the sponge we talked about yesterday, right? That's the organic matrix, the soil structure. Exactly, Blair gave us that example when he had that 8-inch storm event. So every gram is water, massive increase of water. Every gram of extra C, carbon that we can put into our soil, again because it's got this massive matrix of polymerized carbon, it's like a big fan. All of that carbon has massive negative charges all over it, and those negative charges can hold cations, essential nutrients, and hold them in a form that's available to plants. So we massively increase the cation exchange capacity of our soil, which is effectively jargon for saying the available nutrients. In nature, 98% of nutrients are locked up in mineral particles not readily available, because if they are available in the soil solution, as in hydroponic agriculture, hey, they leach, right? They get lost, and then that land just degrades. So nature basically is not that stupid, and it'll basically hold its nutrient either in mineral form or in these cation exchange, you know, I mean, think of it as not a sponge, but as Velcro, right? Here's this massive surface area of Velcro, able to hold zinc, magnesium, manganese, cobalt, copper, selenium, you know, the 33 essential critical nutrients the plant needs, the fungus needs, the plant needs, we need for our health. That's tomorrow again, right? But the point is that that cation exchange capacity is critical to the fertility and productivity of the land. Fertility's got nothing to do with how many nutrients in that soil in total. It's got everything to do with how available those nutrients are to the plant. Okay? And the thing that makes them available is these cation exchange capacities, which is the carbon that you've sequestered in seed. Every gram, okay, gram, and there's nutrients. Every gram carbon we put into the soil increases the structure of the soil, increases the aeration of that soil. Okay, so allows air to percolate through that soil. And so it has a massive effect in allowing roots to penetrate deeper through the soil, to proliferate through the soil. And when you think of it, vastly enhance the volume of soil that plant, that biosystem is using, in its whole health and ecology, right? So rather than roots being restricted to 6 inches, which is where Blaine's sort of cropping neighbours probably are, Blaine's prairie grasses that he's regenerating progressively, they basically put roots down to 3 metres, naturally. Blaine's would probably be down at, 1.5 or something now?
More than that.
More than that. Oh, congratulations. Yeah, okay, but the point is that the volume of mineral earth that is now brought into that biological dynamic and cycle increases exponentially because it's a 3-dimensional soil volume.
I just want to clarify something. So the carbon, or if the soil has more carbon in it, then the carbon, which is negatively charged, is able to pull out the cations, which are positively charged.
It's able to hold those cations and keep them in a form that's readily available for plants to use. To pick up. It's like a credit account. Instead of being in the Reserve Bank, Fort Knox unavailable, it's in your credit account and the plant can use it but not lose it.
Okay. And I guess I thought it was more that there was living things in the soil which had carbon in them, and so therefore those living things actually had some of the
yes,
other
okay, no, they have some
in,
nutrients too, absolutely, yeah.
Okay, and then they traded with
that's part of it. Yeah, no.
Okay, but this is something else.
Well, we're talking about the cation exchange capacity of that matrix, that credit account.
Yeah.
But, okay, well, let's just jump
I mean, if this is not the right time, that's
No, it's always the right time. You're in charge of
this. This is not non-living carbon.
No, okay, very, very interesting. I mean, okay, look, this is important. So there's our soil, there's the world down under. And basically, see, we don't recognise that there's 1 unit of biomass above ground. There's 10 units of biomass below ground in a healthy system, in this natural system, right? And most of this is in, of course, small fungi and bacteria and smaller bugs and what have you. But the biomass is, massively important, right? So 10 times that biomass.
And biomass is
living microbial biomass, right? Okay. 10 times the plant mass. Hello, Chris. How are you? We're just at the right time. Just at the right time. Absolutely.
Hard to believe that is true.
No, because you're going to be up here, you see. Chris will explain this one. Okay, so now the living microbial biomass in volume terms, and that biomass is absolutely fundamental because the whole nutrient dynamics of soils, the fixation of nutrients, the solubilization of nutrients, the accessing of nutrients, the uptake of nutrients, and the cycling of nutrients. Fixing, solubilization, access, uptake, cycling is all driven by these microbes.
Yeah.
Okay? Because we've got dead mineral surfaces, unavailable nutrients. We've got these 5 microbial key processes that take up nutrients. And then we've got some nutrients in the soil solution that David's friends in the hydroponic industry are losing down the drain all the time. Okay? And so that's where nutrients are in soil. But it's these microbial processes of fixation, solubilization, access, uptake, cycling, that this is what this living biomass does. And so they're pumping. Okay, here's the mineral particles, and the mineral particles are stardust with all these cations and what have you embedded in them. And it's the microbes that are solubilizing these and tagging them onto, here's the organic matter matrix, if you like, with all these negative charges. I'm drawing it figuratively. And so that's where your zinc and your magnesium and your copper and your cobalt and your molybdenum
And all
your
of those
selenium
are
and your
now
boron and so
available, bioavailable.
and they're all held then in bioavailable form.
Okay.
So these are your engine driving fertility in your soil, solubilizing from the reserve bank, and only they can do it,
Yep.
and parking it into your credit account, but not
Okay.
leaving it on the footpath where it'll get washed down the street.
Okay.
Pat, sorry, can you repeat what you were saying about what, the hydroponics? That hydroponics?
Okay, well basically, no, good. See, what we've drawn it here. See, so there's 3 stages in a sense. We've got mineral, locked up, unavailable nutrients, stardust, formed 4.6 billion years ago, bang, that's the periodic table. The only thing that unlocks it from these unavailable forms are this living biota, microbial biota, and then as you said, as they die, or they'll park it onto this cation exchange capacity matrix, right? So here's our cation exchange capacity. If we oxidize the carbon, all of this stuff goes into the soil solution, doesn't it? If we burn off all that carbon, all those minerals end up in the soil solution, and of course, if it's in the soil solution, it'll just drain.
Yep.
It'll go into our creeks, and it'll eutrofy and pollute our rivers and lakes. Okay, and so
And
it's
tilling
really,
will accomplish that.
so
Tilling is a major way to oxidize.
and tilling, cultivation, a major way to oxidize. Yep, exactly. You know what you've been always saying.
Salts,
Don't disturb the soil.
biocides.
And yeah, and not just only burning, tillage, fertilization, biocides, fallowing, because fallowing, you're starving these suckers. I mean, these are friends of ours. And,
That's why we can call them suckers.
but the whole point is in the whole, okay, this is important, the whole nutrition of our future health, our future nutrition, feeding 10 billion people, will depend on us managing these finite nutrients and the availability of these nutrients, accessing them, making them available, but then having them in this credit card form on the organic cation exchanges, rather than into just the soil solution where they risk being lost and causing the pollution and the pandemics that kill us, right?
So my question is that matrix, what is my word? Is that the carbon, the dead carbon structure, or is it just a visual for?
No, it's well, I mean, okay. The carbon, this carbon here the carbon is effectively dead. It's a matrix, right? The skeleton. But as we've sort of said and think, there's this massive tenfold biological dynamic life. Of course, it has nutrients in it, but it cycles very rapidly. Like the average bacteria might last 2-3 days, and then its nutrients get parked onto this. So the bugs are taking nutrients from this as well, of course, right? So you've got this very healthy nutrient dynamic. It's very important to explain that in Queensland, Australia, we've got rainforests on sand dunes, which is, of course, a stupid paradox. It can't happen. How can you have the world's most bioproductive terrestrial ecosystem on effectively crushed glass, silicon dioxide? You see, it can't be so, but it is so. I can take it. It's beautiful. And of course, what happens in that case? The bugs are so efficient and so active at cycling those nutrients, at solubilizing and then cycling parts per billion, very, very low levels, that it can sustain a rainforest. But every molecule of phosphorus in that rainforest would move, 1,000 times faster, than the molecule in a conventional agricultural system. And it's 1,000 times faster that is underpinning the productivity.
Isn't it also that the fungi can actually do some mining in the subsoil and break down rocks and break down?
Absolutely, and this is, absolutely, and that's what we call about solubilization, right?
Yeah.
So the fungi, the bacteria and fungi are actually, here's a stardust, here's a locked up, stardust minerals, periodic table, and they're able to selectively solubilize and make available through their process and then park this on this cation exchange. And of course, again, the Amazon, oxisol, glattisol, very, very, unlike our rainforest and sand dune, very, very low nutrient soils in total. But again, it's the fungi solubilizing the iron aluminium oxides and the phosphorus in those iron aluminium oxide that actually allows that rainforest to exist. And again, the whole thing in the Amazon is just driven by these soil fungi.
So one more thing, when you had the sugar cane up there, you said 370 tons, and then down
biomass.
below, huh?
Yeah, a biomass, yeah.
173.
Above,
173
above, 173 below.
And now you're saying 10 times below, so,
No, it didn't.
No, we're talking about different, no, sorry, yeah. We're talking about the plant weight, you know, and how much carbon is in the plant. And okay, well, in that sugar, I haven't measured this, but in the sugar cane, we're saying, okay, there was 173 tons there, 173 tons there, and we're talking, 1,000 tons of living biomass, cytoplasm, you know, in that healthy sugar cane. And
Of the plants, but in this case, you were talking.
Yeah, we're talking about the
microbes.
weight of the fungi, but on the weight of the microorganisms. But what I mean, in that healthy sugar, there could easily be 1,000 tons of microbial biomass in those soils, right?
because I thought you said 30% of that 173 was from the bugs. No. Okay, that's
Well,
okay.
look, okay, so we've had this important, trip into the nutrient future and dynamics, but let's get back to your kindergarten lesson A, B, C, D. Because we haven't finished with the D's, you see. So we've got 1 gram goes into air, which goes into roots, which goes into volume of soil, right? And again, it's that whole point. This is exponential now, as in Plain's case, we're using 2-3 meters of soil rather than 20 centimeters. Enormous powerful thing. And see, it's these things now, these dividends, these multipliers, these positive feedback multipliers that give this system resilience. Remember yesterday we talked about resilience being the longevity of green growth, the capacity for this system to sustain growing, healthy, productive plants over time. You know, how long it can grow, not how fast it can grow. And so that's going to be so fundamental in this sort of climate changing world where we're going to always have extremes. So the buffering resilience is the key thing. You know, because if we can grow for 10 times longer, then it's so much better than growing 20% faster for a very short, limited period. And it's that dividend that gives you the productivity of these biosystems, as we've illustrated with the rainforest, right? But now we've got this really fascinating paradox, isn't it? Because here is nature, through these dividends of extra water, extra nutrients, extra soil structure, extra root growth, extra resilience, extra productivity. Hey, these natural dividends are negating the need for all this stuff. Because we're here above the ground, putting all these inputs into agriculture to try and keep A going, whereas of course nature doesn't do any of that. It's got no Mack trucks, no quarries, no nothing. It just uses this carbon and these multiplier dividends, and it drives productivity of A directly through that. You see, and so we've got now this question of, are we in the B game or are we in the D game? No, it's true, isn't it? And to get to the D game, what do we have to do? C. Okay? Or we have to deposit 50% of this biomass in C, and we generate D automatically, as Mother Nature does. And so Mother Nature, in again creating a biosystem all over this planet on land, 13.9 billion hectares of productive, resilient biosystem, has used D. No Mack trucks, no lime, no fertilizer mining, no John Deere tractors, no Monsantos, it just uses D. And our challenge, our opportunity, the future, is how do we actually just look at these processes and say, okay, where do we want to be? Do we want to be Blaine, who's basically doing C, and he's collecting these dividends, and he's going home and having breakfast after 5 minutes because D's done all the work for him. It's a bit harsh, isn't it, mate?
You make it very difficult for Puritans.
You make it difficult for Puritan.
Yeah.
The work ethic where you've got to sort of slave in.
Yeah.
Well,
Too much
if
free
you want to
time.
enslave yourself, you go for it.
Walter, could you say a little something about microbial mats
Microbial mats.
and how that?
Yeah. Okay, no, let's do that because there's this part of this carbon story and how the carbon with mats and stuff changes the soil structure
Can
and
we
stuff.
take a little break before that? But
Okay,
I'd like
let's
to
do-
take a particular type of break that we did yesterday.
Adam asked the question before the break. Of course, let's talk a little bit about these fungal networks and the microbial life in the soil. And we had another question about, where's this living carbon vis-a-vis structural carbon, right? And we had that actually last time. Remember we said there's 10 times microbial biomass than plants. And of course all of that, most of the weight, 90% of that is cytoplasm, is water, is solutes and what have you. But 10% of that would be actually carbon. And of course as it dies, as the cell walls of all those bacteria, fungi, that's again the glomalin that adds to that glomalin pool. And so, in a sense, we have living carbon, which is all that living biomass, 10 times the weight above the ground. And then we have not dead carbon entirely, but it's matrix carbon. It's like the skeletons, that cation exchange, polymerized framework we're talking about. But we're also now picking up Adam's point where we said, there's 25,000 kilometers per meter cubed of healthy soils. And please understand, not all soils have this. This is top soil, right? And just as we're talking about water hyacinths, this is the top carbon fixer. I'm saying nature has this. And of course, what these fungal hyphae, they're just not there. They're actually very, very important. They're building our soil, and that's where the pedigree is. Because these things then proliferate all around this soil, all over the soil surfaces, and as I said, on those membranes on these soil surfaces, they're absorbing essential nutrients, they're excluding toxic nutrients, they're selectively, intelligently harvesting that soil matrix. Okay, and when we're talking in Regina, it was all about, that soil microbial root interface, because these of course connect back to the root, and they're just taking up nutrients from these surfaces and transporting them to the root. And that's the nutritional aspect that, of course, is much, much more powerful than that, much more important. Because as these hyphal threads grow through soils, they will sort of aggregate soil particles together, right? They'll sort of tie up little balls. Okay, here's our reds. And so this is really, you get massive, it's like a, ball of wool, sort of, really tied up. And these become aggregates, right? And so then soil, instead of being just a random sand, loose sand, like as we talked about out in the desert, so here we now have these aggregates. And of course, that's what we call as beautiful crumb structure in our soil. So we'll have this soil filled up with these little aggregates, all of them tied up with these massive hyphal, networks. And so, the 25,000 kilometers actually then, act as these little aggregating, tie-up little balls. And so our soil, instead of just being loose sand particles or mineral particles, actually ends up with these crumb-structured aggregates. And they're powerfully important because as you pull these aggregates, you actually create, obviously, we'll do that in blue, we can actually then create, here's the air filtering down, here's the water filtering down, here's the roots growing to depth, right? So instead of having just a matrix of soil particle, fairly uniform, it's actually creating a structural world where water, air, roots can proliferate freely. But more importantly, inside these aggregates, you create a completely different microbial ecology, completely different environment. And whereas out here, it might be, 19% oxygen. I mean, there's 21% here above the surface, right? We're breathing 21%. But basically down here in these channels, it might get down to 19%. But inside these aggregates, it can get down to 13% or 10%. And so these aggregates have become, in a sense, partially anaerobic microsites. Okay? So these things become, in a sense, completely new environments. And of course, the fungi can regulate just how much oxygen they let in. They also regulate it by how active they are, because as they're active, they're using some oxygen, and so they can deplete the oxygen inside the aggregates and get it to just sweet spots. You know, they can make this stuff sing and dance for them, for us. And it's very important, you see, because we were talking about loss of carbon from soils by oxidation. But once you get oxygen partial pressure in these microaggregates, getting much below 15 parts per million, or 15%, then oxidation, drops off a cliff, right? I mean, there'll still be some going on, but basically the aggregates themselves reinforce carbon stability, because within these little, oases now, you've got basically a completely different biochemistry, completely different microbial ecology, much reduced carbon oxidation, and so much more stable carbon. Now, see Didi? Didi was saying she was in Oklahoma, and there was a farmer that was basically doing 10 years of, holistic management practices, and yet they haven't been fixing carbon. Because if they've still been at this stage, then the whole thing is still oxidated, right? And it's really a case of at what point do you get to this point of aggregation where you then start saving carbon big time. And of course I imagine Peter would sort of be able to add comment to that. So when you say that there's carbon, there's time, so like Cole Seiss and some of our leading farmers, you'll find that they start off and sure they're fixing carbon, progressively, but then after about 6-7 years, the rate can go up fairly dramatically, because at that stage, the soil is now aggregated well enough that it's actually created these microsites, these anaerobic microsites, where carbon is now much more secure, and the whole thing sort of builds up in carbon further and further. So in a sense, we've got another whole world in soil and this microbial ecology. It's a frontier, it's actually becomes a frontier for nutrition, it becomes a frontier for carbon, it comes, it's how do we manage these aggregation soil structures, how do we manage, the nutrient availability, all that. We know very little about it. I mean, there's some good sort of primary work, but generally speaking, that's really from a microbiology point of view, some of the front line,
Can you say anything about how plant roots interact with these microaggregates?
Okay, so very good question and stuff. And obviously plant roots will grow through, these root canals mainly, right? And that gets to depth. But then, of course, the mycorrhizal fungi, which are effectively extensions of the plant roots, and some of the root hairs will, interface with these. Okay? So they actually, you've just got a diverse microbial habitat with different sites. The other important thing is to say, in terms of nitrogen fixing, because that was something that came up. To fix nitrogen, to fix atmospheric nitrogen into then ammonia, through biological processes, you need anaerobic sites. The legume nodule has to be anaerobic. And these things are not. And so there's a massive level of asymbiotic nitrogen-fixing bugs, which means nitrogen-fixing organisms not directly in nodules, not directly on roots, but they're existing independently. And of course they go right back to 3.5 billion years ago in the oceans, and these are your blue-green algae, your azospirillum, azotobacter, and so there's a vast range of nitrogen fixing. And these things can fix, yes, 60 kilograms per hectare per annum of nitrogen in this soil, providing you that nitrogen nutrition that we're currently just pouring on as nitrate fertilizer and doing a lot of damage. And so we've got grasslands in Australia, paspalum grasslands, very, very productive, and you can't see a legume for miles. And you say, how can this grass be so green, so productive? Because it's driven by these asymbiotic rhizosphere nitrogen fixing bugs. And yes, so basically nature is just exquisitely effective. It creates these different habitats in its soil. It also totally changes the disease conditions, right? Basically, there's antagonistic organisms that form in these aggregates. And so if you have a fusarium or pythium or phytophthora or something like that, then it just can't grow there because there's just so many of these bugs producing antibiotics, preventing it. So you get a very, very dynamic, healthy soil environment.
Yeah, and I guess I was thinking dynamic too, in the sense that if you have an area where you have an aerobic condition, of course, that's going to generate, it's going to use up the oxygen, and then you have anaerobic, and then it's going to reverse that process at some point, and you're going to end up back in aerobic again. So it's a very very dynamic.
Very dynamic, and of course, as Glenn's rightly saying,
the pH should vary too.
Yes,
along with that.
Okay, let's talk on that in a second. Yeah, definitely. Look, the organisms, because they're still using oxygen, they then will help reinforce, because they're depleting the oxygen in these microsites and actually forming these, suitable conditions. Anyway, the bottom line is you get these aggregates, you get very beautiful, deep, crummy soil, and again, we know it because we go in and put our whole hand into the soil up to our elbow and say it's wonderful. Blair said it this morning, he picks up a handful of soil and he smells that soil. What he's smelling is the volatile from the actinomycetes that again, partially anaerobic, right? And these are just blossoming in these things, and he's just smelling those fantastic, beautiful smells. Those actinomycetes, they have given us 98% of our antibiotics that govern our health. I mean, of course, we bastardize them. They're cactus history, because we're breeding antibiotic resistance in our animal production systems. So, sorry, that's a piece of history to go. But the point is that the smell that we can still get in the soil is exactly a reflection. And so when Blaine sort of goes around and says, look, I'm smelling the soil, I can read a lot, he's actually reading a lot of this microbial ecology. And we can sense it, but it's so sophisticated, so complex, we can't actually break down what everything you're smelling is, right? It's very...
I told you I was quite simple.
Yeah. And now, what was the question? Okay, the question about pH. And actually, it's in this sort of same vein. But it's so important because, again, as we sort of said, and I'm just drawing this now figuratively, here's this polymer, this carbon, stable carbon matrix. And as we sort of said, it's got all these negative charges on it. And of course, what is pH? pH is the actual number of hydrogen ions that are in our soil solution. And of course, the more and more hydrogen ions in the soil solution, the more acid that soil is. Okay? And so it's an exponential curve. And so when we get a soil that's going down to pH 4, and we get soils like that in Australia quite a bit, we've got massive number of hydrogen ions. And of course, to try and neutralize those hydrogen ions, to neutralize that acidity, the recommendation is pour on lime. Add lime, add lime. But of course, lime, all you're doing is you're adding a bicarbonate ion, be a 3-. And obviously you say, hang on, how many bicarbonate ions in a linear process do I have to add to neutralize so many positive charged hydrogen ions, which are growing up in an exponential process? Well, you know, you haven't got Mack trucks big enough to do it, nor have you got a bank balance big enough to do it. And even if you did, the calcium toxicity that would result would sort of, you know, kill your soil. But nature doesn't do that again. See, nature says, look, we just have organic matter. As we build out carbon, this can hold all the positive hydrogen ions you like. And so basically the organic matter matrix takes the hydrogen ions out of the soil solution, and bang, your pH goes back up to neutral. You see, and so there's how nature neutralizes acid soils, not through lime, but simply by increasing the surface area, the quantity of carbon in the soil, and then just holds those hydrogen ions in a different innocuous form, and she's sweet again, singing and dancing.
I think it's important to note here that you're using the term anaerobic in a very positive frame.
Yeah.
And most people who talk about soil being anaerobic have a very negative association with that word. But what's going on is a dynamic balance that's shifting back and forth between aerobic and anaerobic conditions.
But it's even better than that, Peter, because look, we've got a soil now where these microbes are orchestrating sites for different functional activities. So no, I want this aerobic because I want air going down to depth. I want, you know, so I've got these highways, I'll keep those aerobic, but these different sites I can manage at different anaerobic conditions. I can manage some which are chock-a-block with actinomycetes as a, you know, and so these microbes, this is the microbial ecology, they can create that diverse world with all these different biochemical functions depending what it is, right? And obviously a massive buffering effect. And again, if you put a fusarium or phytophthora, you know, pathogen in there, it hasn't got a chance. You see? And because again, phytophthora, for example, has to have zoospores that have to swim around in the soil solution to get to a root. Well, basically, yeah, it can't do it, right? There's so much antagonism, there's such a, you know, difficult environment compared to somewhere like here where this is saturated, then the zoospore would easily go infect. So
my understanding is that it actually, they do it for their plant partners. In other words, the plants need certain things, and and so they, what do we call that?
That's a symbiosis. Now, actually, it's an intriguing thing, isn't it? Like it's a chicken and the egg. Are they doing it for their plant partners, or are they doing it for themselves, and their plant partners are there just to feed them? See, so is it really fungi that run this world, and the plants are there, and we're just part of that omnivore that helps cycle some of that plant detritus around, who's running the show?
Well, the complexity is our metaphors, and,
that
we're imposing on something else, which really is a totally different universe from the one that...
And so, Adam, you asked the question, you know, what do these networks do? And, you know, like, does this help? This microbial mat and mass.
Well, I was thinking of literal microbial mats.
Oh, okay, yeah. Well, look, you're in the litter, of course, you'll often get this deep, dense white mat, especially in ectomycorrhizae, breaking down litter. But what I'm saying is, this whole microbial world, it's another world. It's just dynamic, alive. And of course, this is one of the most high-tech biological, chemical warfare environments you could think of, right? Do you understand? Like, I mean, all these actinides, it's all chemical. They're working with volatiles, parts per billion, zapping pathogens and conducing. I mean, so it's a very, very full-on living world, right?
It's a jungle down there.
Yeah. Okay. So it did.
I think your point about the negative associations that we have with anaerobic environments come from our association with organisms that are so-called strict anaerobes, which I have actually cultured in the laboratory for diagnostic purposes. And we associate these things with rotting flesh and the stuff that goes on, you'll excuse me, in all of our intestines. And that's what Walter is talking about is something that's a lot more nuanced, a lot more balanced, and a lot more, well, a lot less strict.
Yeah. But as I take a point, Clostridium botulinum, botulinum toxins and stuff, it needs anaerobic conditions, but no, look, it couldn't survive here. And so it's really like basically here's natural healthy soils acting as an immunological buffer.
Actually, about the botulinum bacterium, it is present in soil. It lives there. It lives in an aerobic phase. It's very happy that way, but it doesn't produce the toxins that can kill the likes of us under those conditions.
Well, that's an interesting point too, to be taking a look at from also other things that, not just botulism, but also things with E. coli and other types of organisms when we're treating manure. And if you use manure as a nutrient amendment, if you've got things you basically take your manure and put it into a pool, the potential that you could have to breed more toxin types of producing E. coli 0157H7, and the toxin from that may be increased in the same way that in botulism that happens, that if under an aerobic condition. So if we utilize grazing, we have a standard on when we can apply manure in comparison to when we're going to be harvesting. But if you're utilizing grazing as a management where the manure is broken down aerobically rather than anaerobically, when you're applying anaerobic manure, you may have a difference in the level of toxins that would be there. So the fact that they do that, you have a standard because of the fear of human-borne diseases, but
it's not flexible enough to deal with the types of farming that are being shown effective.
Right.
But just one point, because we'll have to go for lunch, but basically in terms of our immunity, like most of us grew up as kids on healthy soils, and we were basically immunized by all the organisms on the soils that we crawled over and ate and played in and what have you. And we don't have immunity when we're born. We've got to trigger that immunity, with these agencies. And then we build we build immunity resistance depending on what we get, induced. And so that whole issue of, here's our basis of our immunity, these healthy soils that we, were part of. But nowadays, of course, we're no longer. We're just living on a plastic thing soaked in insecticides, right? Mm-hmm. And what does that do to our health and our immunity down the track? But that's another discussion. Mm-hmm. Now, I hope I haven't put you off lunch with the lobster story. And I'll see you for this lobster for lunch, right? But look, what we had here on before lunch is, and this is important stuff, we'd had various questions about, how do we turn a desert, how do we go and move that process along, now I have tongue-in-cheek, how do we turn that desert into a rainforest, sand dune into a rainforest is doable. And the answer is, it's again, beautifully elegant and simple, and it's, as we sort of heard from Black this morning, it's just a simple matter of growing a plant, right? And so it's a plant, and as we sort of said with that ABCD analysis, right? Every plant, it's the same game. It's just growing a plant, fixing that carbon, which was the A, and then optimizing C, getting the dividends to give you the D process. And so, there's your growing plant. And it doesn't matter if it's a weed or what it is. It's a plant, it's fixing carbon, it's excellent, right? The second thing you have to do then is to say, here's a plant. Now I want to cycle that plant, right? And the best way to cycle it again, remember we have these mobile biodigesters, and the best way is to put it down as excrement, right? Eat it. It's a law of ecology. A law of ecology, foundationally, if you can't beat it, eat it. Right. And that's so important because the whole of ecology was worked on, growing things, photosynthesis, and then cycling that thing, right? And so the point is that the quicker you then can cycle that plant back into dung, and of course the minute you do, and this is another thing about weeds and pioneer plants and regeneration of raw desert soils and stuff, basically by a plant growing in your soil, it creates a new environment. By definition, it's putting carbon and stuff like that. And so it creates a new niche, and invariably, if you've got diverse seeds and other things there, a whole lot of other plants will come up as other successional stages. If not, you can just broadcast a mixture of these successional stages, and they'll come up. So no plant grows without changing its site and creating a habitat for a next successional species. No plant actually is a weed in nature, because every plant excludes itself in nature. It changes its site to make it unsuitable for itself. Okay, and so we can just accelerate this succession, and quite frankly, in very quick measure, we can go, from a bare mineral sand, what Tim sort of raised, into actually more and more carbon, and as the carbon improves, the water improves, the nutrient improves, the resilience improves, the productivity improves. But Elizabeth, you had a...
You just said a great line and I didn't catch all of it. No plant is a weed in nature because every plant
creates change in its habitat, and therefore it creates a new niche for other successional stages. Okay? And so we only see weeds because we kill the plant and we go back to square one to create the same toxic, sterile habitat, and then the same weed tries to get back in there to colonize that plant, and we kill it again. We never learn, it goes back, and Monsanto makes money, it's business.
Yeah, I asked Peter this earlier, and I'm going to ask you now. I look at images of Syria.
Yeah.
And how desperately horrible the land is. You may find one little squiggy tree somewhere.
No, okay, well, Syria,
Syria
is the Fertile Crescent. Syria is the Garden of Eden. Syria is the foundation of agriculture. For 10,000 years, those farmers in Syria have been sustaining agriculture. It's the birthplace of our civilization, our Western civilization. About 40 years ago, they bought the Green Revolution. They bought fertilizer, pesticide, all that high input, cash cropping, make money. You see, and they've been oxidizing and mining their soil. For the last 15 years, the poor peasants in Syria have been abandoning their land because, as Tim said, it's gone to deserts, it's gone to mineral sand, and they've been moving to those, nirvanas of Damascus and Aleppo. You see, and you know what's happening in Damascus and Aleppo. And so it's Jared Diamond, it's collapse, and exactly that. And of course, it's President Roosevelt told you, didn't he? A nation that destroys its soils destroys itself. Full stop. You see? And that was your Dust Bowl experience, that was your Dust Bowl warning, and people just don't pick it up.
That's happened in 40 years in Syria.
Yeah, in Syria, yes, basically in 40 years of high input, moron agriculture. When I say moron, it's M-O-R-E-O-N. I got the wrong word. Okay, but 40 years or more on agriculture, they've oxidized the crap out of their country.
So where to begin to turn that around?
Can I just say one thing? As I said before, I've learned that Walter tells a story from beginning to end, and I'd really like people to hold off on questions for this next half hour and let him hit your questions will get answered. So he's about to say all this.
Okay, but the point is that exactly this pathway, how do you turn that desert back into vegetation? It's exactly let the weeds grow, maximize whatever's green, whatever can grow, and then you start cycling it. Now, obviously, the trouble in the Middle East, they've had 15 goats and 30 eyes looking at every blade of grass coming out of the ground. And of course, as we said before, it's not the herbivores, but it's a rest, right? It's, it's a matter of, we're grazing for 1-2 days of the year, but 364 days, it's resting, it's growing. And it's that rest and the strategic use of that rest is what actually makes the productivity, makes the cycling.
But you can't do it without that one day.
This is actually very important. If you don't have that, here's a grass will grow up, and basically it will then stagnate and get moribund and knotty and stuff. And so unless you have a herbivore that eats it, 90% of it, it'll then rejuvenate and it'll grow again, and you can go about 4 of these cycles, right? And so it'll rejuvenate, 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 and every time that's above ground, and then you go below ground, you got the same thing happening with your roots, right? There's your roots, then you basically eat it, the roots drop off, they'll grow again, and they're growing again, again. And so what you're doing with grazing, intelligently, ecological grazing, you're actually pumping carbon into the soil through this root die-off in successive stages, and also you're pumping bionutrients as these animals are grazing and putting dung back into the soil at each of these cycles, and of course you're pumping protein to feed your kids in the country, right? So, do you understand? Like, I mean, it's the ecological management of that pasture and that grazing, but every time it's a rest period, you know, this is rest and then eat, rest, eat, yeah.
So why 4 cycles?
Oh, no, you keep on going depending how fast the thing regrows, right? It doesn't have to be 4. If it's in Canada, it's 1 or 2, but yeah. Yeah, no, but what I'm saying is you get to a plateau, everything grows to a plateau. Once it's plateau, it's time to recycle it, to regenerate, to reinvigorate. Okay, so really this is, in a sense, you know, regenerating the desert or rebooting, you know, like Syria thing. But actually, we're talking here broad acre, you know, like here's landscapes, and that's valid and that's important and we can do that. But there's another dimension to this whole thing, another niche that's critically important. Over half of us now live in cities, we said that yesterday, and there'll be sort of 70% of us in cities, 80% in cities very soon. And so urban agriculture is again a very powerful, valuable frontier. And this very thing can be done in urban agriculture. And it's so elegant and so simple, and what we call these wicking beds, right? I don't know if you've heard of them here, but in Australia, this is what we're now looking to do for urban, and it's a modular thing, but yeah, you can have any number of combinations, but the idea is give every kid a wicking bed. So it's a little garden box really, 1 metre by 2 metre to say, but what we've done in Australia, we got, it's very cheap, you know, you get these for about $2. You get a sheet of plastic, which then basically ends up as a water reservoir, right? So you have a little water reservoir. And then you put sort of some plant pots in there, just plastic plant pots. And then you have a bit of a mesh above that. And then you put another plastic bag in there, but these will go down the little plant pots, right? And you fill all this up with soil. You know, good organic, mulchy, you know, composty soil where you've made composted soil from your vegetable. And the point is that you can water this thing, and of course the excess water drains down into this water reservoir, but because these plant pots are sitting in that water, this will wick up, you know, water into that soil. And for us it's critically, and a lot of urban environments, it's critical because that way you can get 10 times the bang for your buck out of your water use efficiency, right? You're not draining water away because you're basically saving that water and it's being reused. You only have to water these ones every 2-3 weeks. And the beautiful thing is then we've got this other thing here for urban agriculture, which we call a worm tube, right? And it's really just a plastic bucket that's turned upside down. And of course this is hollow here, right? This is hollow. And every day what you do is all your kitchen scraps and stuff like that, even meat and things like that, it's got a lid on it to keep the blowflies out. I mean, you know, it's just the bottom of the plastic bucket that acts as a lid. And you walk along and you drop your scraps in there. And of course you've got all these worms that are living through the soil, and of course they can hear you coming, you know, they'll hear your footsteps. And no, literally they'll feel the pressure on the footsteps. And they're making a beeline to say, hang on a minute, I want the tucker first, you see. And they'll eat all your scraps, and of course they'll take it out and excrete it all throughout the soil. And
you
so
have
you end
to you have to translate tucker.
Tucker, oh yeah, okay, tucker's food, right? Yeah, tucker's food, right? Sorry, okay.
Bush tucker.
Bush tucker, bush tucker. Okay, so, and if you want to, you can put a glass house, a plastic canopy glass house on this. So what we're giving kids is, in a sense, a microbiome, right? A full-on earth microbiome, where they've got hydrology, they've got worm, they've got nutrient cycling, they've got compost, they've got a controlled environment. The other thing is we can put this, because it's just a box out of old wood and stuff, because basically, okay, what we've been talking about, there might be a big tree here, and there's tree roots, and here's the fungi. And so what the sad thing with most gardens is that people are trying to grow veggies in gardens, in soils where there's trees and mycorrhizal fungi. And as I said, my 25,000 kilometres of fungi basically are eating all the nutrients that would otherwise, you want in your carrots and your vegetables and stuff like that. So what I'm saying, you can't compete with these trees and these mycorrhizal fungi in your garden plot. You've got to have a plastic sheet that separates, them from you, from your garden. Okay? But then in here you can actually sort of absolutely beautifully productive vegetables. But the point about this is social empowerment, right? That all the kids, any old people, anybody can say, look, here's my urban green garden. And I make the point that, there's urban agriculture, the urban recycling of nutrients. It's just so critical, because as food security gets more serious, certainly we're going to grow protein, broadacre, we're going to grow grains, broadacre, but a lot of that green, high nutrition vegetable is going to be related to, what we can grow in these urban areas through these very elegant, simple technologies. The biggest issue, though, is how do we empower youth, children, schools, everybody to say, hey, we can do this. We can manufacture these for a couple of dollars as little eco-industries out of waste material. And it's the real social empowerment of urban agriculture, green gardening, enormously important, right? Okay, so regenerating our, degraded lands and really building food, whether we're broadacre or whether we're in the urban area, yes, we can. It's all doable. Paula.
Just a quick question, because urban soils are often so toxic.
Okay. Well, urban soils are often so toxic. Yes, you're right, but basically if we take any urban subsoil, if you like, don't take the first 5 centimetres, because that's where heavy metals and polyaromatic carbons and stuff might be. But if you take any subsoil and you mix that with compost that you've got from organic waste, 50-50, and you put it in there in no time, you've got healthy, productive soils. And this is actually something that we should talk about briefly, the whole thing about healthy soils, okay? Beautiful word, healthy soils, we'll go with it, and then if you're asked to say, well, what's a healthy soil? And it's a bit nebulous, isn't it? How do you define it? And in a sense, we don't want to get too technical, but as we've sort of said today, A, B, C, D, see, a healthy soil is a soil that addresses the limiting factors that are actually impeding otherwise plant growth, right? So has it got the water, has it got the nutrients, has it got the rooting aeration environment, has it got the microbial cycling, has it providing all those things to overcome the limiting factors? And so I think that's something that's going to be important, because coming to the next topic, we'll talk briefly, because I think now soils are being recognised as a key, valuable asset, a tool for regeneration, a tool for carbon drawdown. And so we'll be saying, okay, healthy soils, but the answer is what constitutes a healthy soil? And as we say, infiltration, water retention, availability of water, longevity of green. Nutritionally, remember we went through them? Yes, this is soils that's fixing nutrients, solubilizing nutrients, nutrients are accessible because of these high feed. The uptake's happening and the cycling's happening. Aeration, same story. Okay, so these are just the factors we talked about in ABC, and if those conditions are there, that soil will sing and dance for you, with you. And of course, that's a healthy soil. Okay, one other topic that was on that other page then was this whole question of, COP21, Marrakesh, COP22, and really what's happening out of that process. I imagine some of the groups might have talked about that at lunchtime, but if not, it's the UN thing, it's in process. But the big thing was that Christina Figueres at COP21 Paris last year, it was a massive breakthrough, right? Because for the first time we got the acceptance of zero net emissions. And it's that little word net that was a breakthrough, right? Because for 50 years we've been talking about we must reduce emissions, and we've been flogging ourselves, as we saw on that Keeling curve, hey, we've got to stop that emissions. But the message is, no, we've got to actually re-green, regenerate, re-enhance our drawdown capacity. And the net was a message to nations and people all over the world to say, look, it's drawdown, and that counts just as much as emission reduction. Of course we have to reduce emissions, no question about that, but we can also draw down. 197 nations signed up to COP21, and sure, we've got the dirty dozen, you know, that massively net emitters, but we've also got some 180 nations who can very rapidly see, hang on, we can offset many of our emissions, we can be in net positive very rapidly. And Blaine mentioned that this morning, okay? Trudeau in Canada now says here's a carbon tax, here's a carbon price, and now everybody in Western Canada is saying, hang on a minute, this is revolutionary, right? We're going to be suffering. But on the other hand, it's just a question of accounting, because with zero net, you see the question is, all right, I'll pay a carbon price on my net, and if I'm in positive, I'll be sending an invoice to Ottawa. So the message is invoices to Ottawa, because we're basically, you know, going to be in positive, and we can be in positive through these processes that we talked about. You know, if you're doing 5-10 tons carbon per hectare per annum, then you're going to be basically drawing down more carbon than you'll ever be emitting in that industry, and you'll be sending an invoice to Ottawa. Yeah, and so that's really the big picture. Now with the UN, for that discussion group, and please, you know, let me know if there's other points raised, but with the thing, okay, it's a very slow process, glacial process, and of course it won't happen easy, and we don't know quite the politics, because obviously there's a new president in America and stuff, but whatever happens, we've got 197 nations committed. That's going to go on, and no matter which way, you know, the journey takes and the outcomes are, it will be perhaps 2-3 years, and we're looking to see there will be a global commercial carbon accounting mechanism and a carbon price, and then basically 180 nations and states and lots of people will be saying, okay, I can produce and trade offsets, and as Blaine sort of said, we can now then look at, yeah, you know, do we get $200 per hectare per annum net additional income from that carbon sequestration process, right? Your key business is still stewardship of your soil, hydrology, food production, resilience, but there's a $200 carbon bonus. You're not going to do it to get the bonus, you're going to do it to rebuild the sponge, to give you the water, the food, resilience. But basically that $200 really is very powerful at revitalising your farm viability, but also the viability of that regional economy. Every dollar you spend in your regional economy has a social multiplier effect of 3 to 4. Well, that's what it is in Australia, but I'm sure it's much the same here in country of, you know, North America. And so every dollar you spend really benefits that social dynamism, viability, health of that community. So we see this zero net, COP21, and the process after as a fundamental game changer. We in Australia, we produce about 2.3 billion tonnes of carbon a year at the moment from our natural biosystem. We, Healthy Soils Australia, Michael Jeffrey, Soils for Life, no, we think we can double that, regenerative agriculture. You know, there's another 2 billion tonnes. And as we said before, we've got a target of 20 billion tonnes globally to get that CO2 game going downwards.
And what are your emissions?
what we what we admit to and what we bullshit is
Leave out the
to.
cold.
Okay, now look, our formal accountable emissions are 150 million tonnes of carbon per annum, right? That's our Kyoto accountable emission. But of course we also export about 500 million tonnes of coal. And this is what's going to change, and America, be careful, because at the moment we're just dumping dirty coal on other markets and saying, hey, they have to wear that. Well, they're not going to wear that much longer. And so we've got to have the capacity to offset, you know, the carbon in that dirty coal. Otherwise, we're going to get discounted for what we get for that coal. Okay, so the age of externalization liabilities is coming to an end. Thank God. And this is all part of it, right? Okay, the two last things I wanted to say here, and the first one was, of course, with this COP21 and the whole carbon accounting, we're going to need to be able to measure carbon. We're going to need to account for it, and it'll be happening at a global level. And very innovative progress in that area, and it's basically using satellites to measure stable soil carbon increments all over the planet from satellite. Basically every 8 days we've got satellites, you know, mapping every part of the Earth, and obviously they're able to record things to the 100-meter pixel sort of level to 3 meters depth now with the new hardware up there. And so it's just a question of, okay, we haven't got the algorithms, we haven't got the equations to relate that electromagnetic radiation back to soil carbon, but it's doable and not impossible at all. So once we get the Marrakesh or post-COP21 carbon trading systems, then I'm certain we will end up with those satellite measurement methods. They'll of course be ground truth in every key soil types and stuff, with the sort of soil analysis, soil sampling, verification, calibration curves that are happening on the ground. But again, we'll be in a whole new world of, you know, carbon accounting. The last point is actually really something I wanted to perhaps make for our friends from Washington. And basically 6 years ago, we in Australia again had a carbon price, and we were working very directly with our Prime Minister and our government at the time. And we went through a process and put various options there. And this was very, I mean, it was fully endorsed and stuff like that, but it actually wasn't accepted. I'll explain it. And what we called it was a net emissions reduction incentive. That was just the word that we used. But it was really sort of providing an incentive to actually make the whole innovation, make the whole change. But the powerful thing here, at no cost to government, at no cost to the consumer. Okay, so how do we transition to a post-carbon economy at no cost to government, no cost to consumer? And it was very simple. If this is dollars and this is time, what it was is that we would just give people a certain lag phase, a certain sort of forward warning, that after period A, there would be a progressive annual increase in either the price of carbon, actually, or it's gone past that now, the actual reduction in subsidy, the reduction in externality subsidy. So we will be withdrawing, you know, the taxpayer subsidy. At the moment, hundreds of billions of dollars are spent globally every year on subsidising fossil fuel use, and of course we would be withdrawing it, and so in a sense the price of that would go up until it hit sort of basically international parity or some plateau agreed Congress or in our Parliament. And the powerful thing with this concept, and James Hansen, of course, has submitted something very, very similar to this as part of his whole strategy. The powerful thing, if you're a firm here, then you sort of realise to say, yeah, look, in 2 years' time, I will be up for increasing carbon cost. In fact, it's going to start costing me more, or I'm going to get less subsidy. So straight away the government is getting savings or income, right? Because basically the polluters or externality costs are now coming into the marketplace. And that firm is going to be very strategically making a decision to say, well look, if it got up to there, I'm really losing competitive advantage, I'm losing my competitive edge, I can't survive. So the smart thing is, before it got to that time, back here, I might want to invest in innovation. Okay, and if I invest in innovation to reduce my energy use, or I reduce, rather than innovation there, I'm making a joint venture deal with farmers to get drawdown offsets. Okay, so but if I'm basically investing commercially in innovation here, then I can in a sense avoid this price escalation, right? Because this is based on net. So as long as I invest to get rid of enough of my emissions liability, I'm basically going to be able to avoid this price increase. I'm also, because of this innovation, mostly going to be able to operate more efficiently, because, you know, my energy intensity or whatever isn't as high. And if I'm smart, and these are smart capitalistic businesses of course, if I'm smart, if I'm getting a saving, I can actually lower my prices, or at least I can stay, you know, competitive at that price. And if I lower my price, then all my competitors who haven't done this innovation will be massively disadvantaged vis-a-vis me, because they're going to have this increased, you know, carbon price or increased externality payment. And so invariably all you need is a lead innovator in each sector to be the circuit breaker, and then of course that whole sector won't be imposing, you know, that increased carbon cost on the consumers. And so if the government invests some of that money into catalysing these innovations, it should be able to sort of, you know, drive this sort of carbon change, but basically with savings to the government, because the prices are capped here at no inflationary pressure to the consumer. And it's this sort of concept that actually is now being considered, you know, like in the context of the COP21 and the basically introduction of carbon pricing and trading globally. And you've got to see this globally, where nations and firms are really saying, hey, I want to get ahead of the game, I want to innovate, I want to co-invest in drawdown, because I'm going to be more fitter than all my competitors in this game as this happens. And in Australia we're getting lots of inquiries, big money, can we invest in part of that drawdown story to cover their future competitiveness in this post-carbon accounting world. So again, there's solutions, very elegant, very efficient, and really it's part of the future.
Is that still on?
Well, yeah, no, it's still in there, and it's still being talked, and reserve banks, and, you know, sort of your senior.
Because you went through a phase where you actually had a carbon
tax.
tax.
Well, we put this up when we had the carbon tax, but of course it's politics. And what happened, our treasurer, you know, they basically said, look, we just wanted revenue, right? So they weren't interested in changing the thing, they just wanted income, right? Yeah. So they put a carbon tax, which was just a revenue raising money, and it was then, didn't have this part of it, but it failed, right, because the next government threw it out. Right. But the point is that, you know, that's just a blip in the road, pothole in the road. Down the track it's unavoidable, but all I'm just saying, there are very, very clever, stunning, innovative ways, no cost to government, savings to the government, driving innovation, no cost, no inflation to the public. Okay, so look, that was that part. Any questions briefly, or otherwise we go on with?
No, that's great, but if you could, if there's a paper on that, then I'd love to see it. Because we're working on some, it's similar, but it's different, so we're looking at clean tax cuts.
Okay, well look, yeah, we did in 2010, we exactly went to the Prime and everyone, and again, all the economic, all the nerds, you know, all the econometrics that the people crunched it, couldn't fault it,
Yeah.
but of course politics took over. James Hansen, I mean, I'm sure you know, has put up a similar thing, except he's always in America said, okay, the money we get from this, should redistribute back to every citizen on a pro rata per personal basis to help them afford the increased prices from the carbon tax. And I mean, the sentiment is genuine and nice, but it's counterproductive, isn't it? Because you want to avoid that inflationary thing in the first place. What you want to do is want to drive this innovation, right?
Yeah, that's what we're working
Yeah, no, but certainly.
And then if there is anything that you have on the actual, and with the agricultural piece of how you measure how a farm is doing well in order to be able to provide those.
Okay, well, with the measurement of carbon at each farm level, it's very, very simple. As I said, we've got motor satellite every 8 days measuring, the green and the water and all that sort of stuff. And all we need is, an equation that translates what that satellite is seeing and translate that to stable soil carbon increment. Yes, we can do that, like there's 99.9% on that, but no, it hasn't been published and made sort of wider because at the moment there isn't a market for it, right? It's a sort of chicken and the egg. Until we get a carbon market and we know what the specifications on the carbon market is, we don't know how to write the formula, right? Do you understand? So, yeah.
Speaking of carbon monitoring and how do you do that, I mean, we do have some people here that have done that, but as far as, I've been investigating some other ways of maybe doing that, and I haven't got too far. In Ohio, there's a lot of concern about the quality of farmland, of the lakes and rivers and streams because of farmland runoff. And so there have been models that have popped up under USDA, or also there's an institute in Tiffin, Ohio, that has developed some modeling too. But in addition to that, they have, it looks to me like there may be predictive value for carbon. So in sort of deciding what projects to do, there are tools there's a COMET tool that that USDA has. I've looked at that. I wouldn't want to fill out that.
No.
And it's a mess. But I think that seemed kind of hopeful when I was looking at it. So I don't know if anybody has any information on that. I'm very interested in if there are ways of modeling what you're cropping to, and how that might also generate carbon, because there is a fund that is in my town of Oberlin that is willing to give money for farmers to do that, but they don't. This USDA tool is pretty crappy.
For 20 years we've had this dog's breakfast, basically carbon greenhouse accounting, right? It's a real quagmire nightmare. You don't even want to smell it, And the point is that, it's just all the rules, additionality, permanent. There's just so much garbage. And really, we've got to cut through all of that and really say, okay, and of course all the different nations are trying to screw it and fudge it and, misinform. So there's enormous dirty stuff. We had the clean development mechanism under Kyoto, and that was just a rort on a rort on a rort. And but we've got to get to this international, objective, credible standard, and we can. And okay, we've gone through this dirty, journey, and okay, we've got to come out clean, and we can, Okay, look, I might just leave it there then, and then we'll go on to step 2, right?
Okay.